Okay, let me check. Yes, I think we are live. Welcome, everyone. Thank you for joining us today for today's very special webinar. My name is Alejandro Cárdenas Avendaño, and I'm going to be your host. Today, we're presenting Geometrodynamics, the nonlinear dynamics of curved empty spacetime by Professor Kip Thorne. He did his bachelor at Caltech University, and then he went to earn a PhD from Princeton under the supervision of John Wheeler, the very famous John Wheeler. His thesis title was Geometrodynamics of Cylindrical Systems, which is going to be a topic related to today's webinar. Because of his wonderful and great academics, he became one of the youngest professors ever to be appointed at Caltech. And he remains of one of the leading astrophysicists in modern era. And in recognition of all those efforts, he has won many prizes. And in particular, he was appointed by Caltech in 1991 as the Feynman Professor of Theoretical Physics. As I said, he has won several prestigious prizes. I will just mention three, in particular, the Julius Edgar Lilienfeld Prize, the Einstein Medal, and of course, 3 years ago, the 2017 Nobel Prize in Physics, along with Rainer Weiss. He was also a law physics speaker, Barry Barish, for their decisive contributions to the LIGO detector and the observation of gravitational waves. I'm very happy to have here Kip, in particular because where he is particularly early. So we really appreciate that he woke up very early this morning. And for everybody that's listening us today, remember that you can ask questions over email through our YouTube channel or Twitter. And then the questions will be read at the end of the talk. Now, without further ado, we will turn into time to Kip. Thank you for joining us and enjoy today's webinar.
Thank you, Alejandro. It's a great pleasure to be here and to give this webinar. I hope you enjoy it. I'm on the South Oregon coast in a small town hiding from the COVID virus. The internet is not perfect, and so I'll hope that it stays up well through the whole talk. Let me share my screen and then bring up my talk. Get rid of that. Okay, so you see my screen, I presume.
Yes, yeah, okay. Now it's full screen.
Okay, so I want to talk about a topic that I first learned about from John Wheeler, my PhD advisor. He coined this phrase, geometrodynamics, the nonlinear dynamics of curved space-time, 60 years ago. This is a photograph that I took of him lecturing at a birthday party for Willie Fowler, who was a great physicist at Caltech of that same era. He would put all over the blackboard. Of course, this was before PowerPoint, before view graphs. And so he would draw colored chalk drawings all over the blackboard and then lecture about what he had drawn on the blackboard. And what he said to us 60 years ago is that one of the most interesting topics in physics that he would hope that we would figure out how to explore is the dynamics of curved space-time when it is highly nonlinear and rapidly changing. And he called this geometrodynamics. And he challenged us to explore how the nonlinearities in general relativity influence this dynamics of geometry. Now, we know that nonlinear dynamics is a really interesting and rich topic elsewhere in physics. We see it in the turbulence of fluids, tornadoes, phase transitions in condensed matter, nonlinear optics. Modern optical technology is largely based on nonlinear dynamics. Colliding solitons in fluids and plasmas, in nonlinear crystals and optical fibers, chaotic maps and strange attractors in mathematical physics. And so the question then is, are there similar phenomena? Is there great richness of phenomena that arise from nonlinear dynamics in general relativity, dynamics of curved space-time? Wheeler's students, postdocs, colleagues tried to study this, but there were 4 decades of extreme frustration. The first issue is that analytical techniques gave very little progress. The We just didn't have the tools analytically to explore geometrodynamics. Wheeler actually foresaw this, and he encouraged his students, postdocs, and colleagues to develop numerical relativity in order to be able to get a handle on geometrodynamics. This took 4 decades of sweat and struggle to near fruition, numerical relativity. It got close to fruition in about 2000, and 15 more years up to about 2014 to really reach maturity. What I'm going to tell you about are things that we have learned about geometrodynamics from numerical relativity in 4 different, and plus then after you see things in numerical relativity and numerical simulations, things that we have then learned further on by going back to analytical calculations, going back and forth between the numerical simulations and the analytical calculations. I'm going to talk about this in 4 arenas. The first is geometrodynamics near singularities in space-time, nonlinear self-coupling of gravitational waves in what is called critical gravitational collapse, colliding black holes, where the black hole collisions create what I like to call a storm in the geometry of space-time, and finally, gravitational waves observations of geometrodynamics. So this is where I'm going. So let me begin with geometrodynamics near space-time singularities. Let me go way back in history to 1939, the famous work of Robert Oppenheimer and his student Hartland Snyder, where they studied the gravitational collapse, the implosion of a sphere or a ball made of dust. They made it of dust so they could do the analytical calculations so that it had vanishing pressure. And they saw the star in their analytical calculations shrink smaller and smaller until finally it created what we now know as a horizon around itself, though they barely understood what they were seeing. The key thing is a singularity at the center of what we now call a black hole. Now, and of course, we're all familiar with the fact that there are great tidal forces near the black hole or near the singularity that stretch my wife, Carolee, she always gives me permission to use her, stretch her from head to foot and squeeze her from the sides. And that's the characteristic of the gravitational field that I really want to focus on, is this so-called tidal stretching and squeezing. The question then from 1939 into the 1960s is, do singularities really form in nature? After all, this was a calculation that was done in spherical symmetry with extremely high symmetry. And if you throw away that symmetry, do you still get singularities? Two of the people who struggled with this early were Yevgeny Lifshitz and Isaac Kalatnikov in Moscow. And in 1960, through a series of long and very complicated perturbation theory calculations, basically, they came up with the answer, no, singularities are not generic. And they embodied this in the famous Landau-Lifshitz textbook, The Classical Theory of Fields, beginning in the English with the 1962 revised 2nd edition, from which I learned relativity myself as a graduate student. Section 110 is all about the absence of singularities in the general cosmological solution. What they really meant is in the general solution of the vacuum Einstein field equations. It was a great shock to them in 1965, when Roger Penrose in London wrote a classic paper for which he got the Nobel Prize this year, in which he proved his most important result, I think, was to use differential topology. He brought this into relativity theory for the first time, and used it to show that if you got a region of space-time where light was trapped, which basically meant a black hole, then inside that black hole, time-like whirl lines would end. He couldn't say why they would end, but he was able to prove that they did end, that if you fell into the black hole, you would cease to exist, basically. And he could not say anything about the geometrodynamics near this singularity where time-like whirl lines end. He'd simply say there was a singularity definitively. Now this created great consternation, great unhappiness in Moscow in 65 to 69. And Kalatnikov and Lifshitz brought on a young graduate student, Belinsky, to work on this problem. And they ultimately found an error in their calculations and found something really quite remarkable as when they corrected their error. This is just a photograph of myself here with John Wheeler, Yevgeny Lifshitz, Isaac Kalatnikov, and Vladimir Belinsky at a dinner at Kalatnikov's home back about 1972. So the key issue then is what is the nature of the singularity? And what Belinsky, Kalatnikov, and Lifshitz did is they did not look specifically at the interior of a black hole. They simply asked what would be the dynamics of curved space-time, the geometrodynamics, near a generic space-like singularity. And what they found remarkably was that as you neared this space-like singularity, there was a spatial decoupling between what was going on, say, as seen by an observer. I'm plotting time upwards, of course, in space horizontally. What was going on is seen by an observer moving along this world line, observer along that world line, parallel world lines, at least initially parallel world lines, as they head toward the singularity. And the physics of what they saw would become decoupled, and so everything could be turned into ordinary differential equations in time. The same differential equations, but decoupled evolutions along different world lines. And what they found was that the temporal dynamics is what had been seen previously by Charlie Misner and by Belinsky and Kalatnikov, what we call mixed master dynamics. And this was a dynamics on which they found matter has negligible influence. To describe the dynamics, I want to look at the stretch and squeeze produced by the tidal field. Now, the tidal field in Newtonian theory is the gradient of the gravitational acceleration. So it's a second rank symmetric and trace-free tensor in vacuum. If we look at two neighboring particles with a separation vector c, they have a relative acceleration that is given by the product of the separation vector and the tidal field. So delta A, the relative acceleration, is minus the tidal field times the separation vector. And so if you then ask yourself what this means, what it means is that there are some, the second rank symmetric tensor, which turns out in relativity to be the space-time part of the Riemann tensor. It has three principal axes. They're the directions of eigenvectors of the tidal field. And if those axes are, for example, along my head, my head and feet, so up, down, and horizontally to the sides, then these are the principal axes of stretching and squeezing, the tidal stretching and squeezing. And so I'm stretched from head to foot and squeezed from the sides, then I'm stretched to the sides and squeezed from head to foot. And the magnitude of that stretching and squeezing is proportional to the eigenvalues associated with the eigenvectors of the principal axes of the tidal field. So I'm plotting here the eigenvalues then upward associated with the principal axes of up, down, east, west, and north, south. And what they found as you approach the singularity is a pattern where on the east-west direction, there was a squeeze, 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 squeeze. And then in the up, down, north, south directions, there were oscillatory stretches and squeezes for a number of cycles. And then that set of cycles ended and a new, what they called era began. The principal axes of the tidal field rotated around, so you had new directions of stretch and squeeze, and the pattern then repeated. Except the pattern, in fact, was described by what a mathematician today would call a chaotic map. It was a continued fraction map, more precisely. But this was quite surprising then, that you had chaos in the mathematical sense of the word chaos as you approach this singularity. the chaos had a different pattern, different details in adjacent regions spatially. There's different people moving into the singularity, decoupled from each other causally. There was great skepticism about this prediction in the West. This is now in the early 1970s, because the techniques that the Russians used to prove this were perturbation theory techniques, and it was a number of different perturbation expansions that you had to go from one to another. Was had nothing like the rigor of Roger Penrose's work proving that singularities occur inside black holes. So this came to be called the BKL, for Belinsky-Kalatnikov-Lifshitz conjecture, and physicists in the West began to say this is a conjecture that is made on the basis of heuristic arguments. Ultimately, numerical relativity became sufficiently mature that it was possible to test this conjecture by numerical simulations. And so a program of such simulations was formulated by Beverly Berger and Vince Moncrief in 1994, carried out by Berger, Moncrief, Garfinkel, Jim Eisenberg, Weaver from 1994 onward, with Garfinkel really having the biggest impact. And then what was discovered was then studied analytically once the results of simulations had been seen. But the bottom line was that this BKL, chaotic behavior of the tidal forces, was confirmed, largely confirmed, except for basically a few missing spikes in some of these stretches and squeezes, which were interesting in and of themselves, that were discovered numerically, then understood analytically. But the basic picture was as BKL had argued it would be. More recently, there's been a discovery of a different type of generic singularity, a null generic singularity, that I'm going to just describe heuristically in a manner that I do in my book about the science of the movie Interstellar, because this plays a role in Interstellar. So this is an embedding diagram showing the curvature of space as seen from a higher dimension, an embedding space, around a black hole, the usual throat with the external universe up here, the usual throat going down to the horizon. And in the movie, Matthew McConaughey goes through the horizon and is headed toward what would be the BKL singularity in the center. But rather remarkably, in 1994, Eric Poisson and Werner Israel in Canada discovered that in the way I'm describing it, basically, after Matthew McConaughey playing Cooper in the movie has fallen through the horizon, everything else that falls into the black hole over essentially the entire future history of the black hole comes crashing down on top of him in the form of a shock wave because of the huge difference in the structure of time inside the black hole and outside, comes crashing down on top of him in the form of a shock wave that I like to call an infalling singularity, but they called a mass inflation singularity. This, in technical terms, this shock wave is occurring along the ingoing Cauchy horizon inside the black hole. And what then was also found, and a key point about this shock wave is if it catches up with McConaughey, he'll be stretched, say, in the up-down direction, squeezed in the north, south, and east-west directions, with tidal force that diverges, but the second time integral of the tidal force is finite, which means that by the time the singularity hits him, he's only been stretched and squeezed by a finite amount. And so one is left open to speculate about what really happens to him. It was a bit of a surprise in 2012 when Donald Muralf and Amos Ori at University of California, Santa Barbara, and at the Technion in Israel found that essentially everything that fell into the black hole before McConaughey did, some portion of it is scattered back and forms an outflying shock wave or an outflying singularity or a shock singularity, which has this same behavior that the second time integral of the tidal force is finite. And so we now do believe, we think there are three different singularities inside a black hole, one of them with chaotic dynamics, the other with a very simple dynamics, one of them space-like, the other's null. But we don't know for absolutely sure that the picture I'm describing is correct. Numerical simulations are needed to really pin down the relationship between these singularities and whether these things that are discovered by perturbation theory, whether we really are understanding them properly. And some numerical relativists, including Franz Pretorius at Princeton, are now embarking on these simulations. So let me very briefly talk about another area then, the second area in which geometrodynamics has been explored, and this is in imploding waves. This is all rather old work. It's familiar to many of you in the audience, probably not to others, familiar to those of you who work in general relativity. But I think it's important to me to go back and review these things because they begin to give us an overall picture of what geometrodynamics is all about. So this is work that was begun by Matthew Choptuik back in 1993, in which he explored what happens if you have a scalar wave, so a hypothetical scalar wave that implodes spherically toward a center. And so I here removing one dimension, so we only see the scalar wave as though it's a circular wave imploding toward the center instead of spherical, but it's really spherical. And he gave this wave a very simple waveform and a free parameter, the height of the wave. And the key thing that he wanted to explore is as the scalar wave imploded, and this is a calculation done in general relativity, the energy of the scalar wave would create space-time curvature, and then the wave itself would interact with that curvature. So the nonlinearities would arise in that way. The wave was a linear wave, but it interacted with itself by creating space-time curvature. That's created by the square of the scalar wave, basically. The energy and momentum are proportional to the square of the wave. Creates space-time curvature, and the wave interacts with the curvature. And he found a rather remarkable phenomenon, that there was some critical amplitude for the wave, such as if the amplitude of the wave was larger than that critical amplitude, the wave would go in, it would interact with itself, and but its interaction, and it would produce, let me start over again. The wave would go in, and the energy in that wave was so strong that it would generate a black hole. And the mass of the black hole was proportional to the amount by which the wave amplitude exceeds the critical amplitude raised to some power, which is a critical exponent, like critical exponents that occur in phase transitions in condensed matter physics. That power, he found, was 0.374 through numerical work. And if the amplitude was less than the critical amplitude, then the waves would go in, they would interact with each other, and then they would not quite form a black hole, and they would disperse. And the radius of curvature of space-time, this is from the Riemann tensor, you construct this thing, which is the radius of curvature of space-time. At the point where that radius of curvature became the smallest that it could, so the biggest, most extreme curvature, the radius of curvature got very small. It was proportional to the difference between the critical amplitude and the actual amplitude raised to this same power. Again, the same kind of critical exponent phenomenon. And when the amplitude was equal to the critical amplitude, the wave went in, self-interacted, and basically space-time went into an organized frothing, an organized type sort of thing like boiling. And then the wave started to come back out, and it came back out in a form that I draw heuristically like this, a form that was discretely self-similar in a mathematical sense. So this is really quite a very interesting geometrodynamical behavior. Well, what does that have to do with the real universe? We don't see scalar waves of massless scalar waves of the sort that he used here. But this was a toy problem, and the next step was to go in and do the same thing with gravitational waves. Now, you can't implode a gravitational wave spherically. No gravitational wave can be spherical. And so it was Andrew Abrahams and Matt Evans, and then Yevgeny Sorkin, ultimately in 2011 for Sorkin's work, who did this then with gravitational waves imploding axisymmetrically, not spherically symmetrically. But they went in, they interacted through nonlinear self-coupling via the nonlinear Einstein equations, and they found precisely the same thing to within the accuracy of their calculations. The formation of black holes, the same critical exponent to within their numerical accuracy, the same dispersal of the wave if the amplitude was less than the critical amplitude, the same critical exponent, and evidence for discrete self-similarity when the amplitude was equal to the critical amplitude. Since then, there's been a lot of work on imploding other kinds of things and seeing what kind of critical behavior occurs in general relativity. And it's much richer than this if you deal with things other than gravitational waves or scalar waves. But this has become a very significant area of research in general relativity, understanding this critical behavior, very similar to what you see in phase transitions in condensed matter physics. Let me now turn to my third venue for geometrodynamics. Black hole, and this venue involves black holes. And I remind you that black holes are made from warped space-time. And so here is an embedding diagram for a black hole where the shape of space-time is like this is seen in the embedding space. The color coding shows the slowing of time near the horizon. The horizon is down here where it's black at the bottom, and dragging of inertial frames, which is rather like dragging of space into a whirling motion with angular velocity proportional to the lengths of these arrows. So this is an embedding diagram for an equatorial slice through a Kerr black hole, a rapidly spinning Kerr black hole. And what I want to do then is return to the topic that John Wheeler actually hit, that his students pioneered, geometrodynamics in colliding black holes. Just to remind you that collisions of black holes are the most violent events in the universe. These were drawings that were made by an artist when we were just beginning to work on LIGO, of what you might expect would happen for black holes spiraling together, colliding and merging, gravitational waves coming off. What we now know is that the power output in gravitational waves from a black hole merge like this is 50 times higher than the luminosity of all the stars in the universe put together, but only for a very short time, a fraction of a second in the case of black holes that weigh a few times the mass of the sun. And no electromagnetic waves are emitted whatsoever, of course, except if there is a disturbed accretion disk around the black hole, then you can get electromagnetic waves. The details of the collision, the geometrodynamics, are encoded in the gravitational waves waveforms. And so simulations of black hole mergers like this are now a rather routine kind of thing for numerical relativists to do, though it required many decades to make the technology good enough. It was Franz Pretorius who did the first successful simulation back in 1994, I think, or 2004, I think it was. This is the simulation of the colliding black hole that produced the gravitational waves that LIGO first detected. GW150914 is the name of that observed gravitational wave burst. And this is a simulation by the SXS collaboration, the Caltech Cornell collaboration. And what I'm going to show you is a depiction of the space-time metric, that is the geometry of space-time in the orbital plane. So that's a two-dimensional surface in space and slowing of time. So this is an embedding diagram then for that orbital plane, except it's a pseudo-embedding diagram. We know that any two-dimensional surface, which is what we're dealing with here, can be embedded in a three-dimensional flat space, a Euclidean space or a Minkowski space. Euclidean in this case will do is what you need. But the trouble is that if you go around the black hole and come back, the embedding does not match up smoothly. You can do an embedding locally, but not globally. And so what's done here is something slightly different. We can think of it as an embedding diagram for the two black holes that are going around each other, embedding diagram of the orbital plane. What's actually plotted, and this is a visualization by Harold Pfeiffer, who's now at the Albert Einstein Institute in Golem, is the scalar curvature of that two-dimensional surface, the orbital plane, 1 over the scalar curvature to the 1/2 power. That gives you something that has dimensions of a length. And then minus the sign of the spatial curvature. So when it's going down, that means it's a positive spatial curvature. But this looks basically like a true embedding diagram would look if you didn't have this problem of going around and things not matching up quite properly. And so this is a famous movie, I think that many of you will have seen. The movie is slowed down now as the black holes are about to collide and merge. And we watch as the shape of space goes into a giant wave, like a splash in a storm at sea. And the color coding showing the slowing of time oscillates as well, and the gravitational waves go flying out. And so this was geometrodynamics as seen through a pseudo-embedding diagram. The trouble with this, however, is that this depicts much too little of the space-time geometry. The space-time geometry is much richer than what you can see in this kind of embedding diagram. And so in order to visualize the geometrodynamics in considerably more detail, a number of former Caltech graduate students and postdocs and I developed a way to visualize the vacuum Riemann curvature tensor, which is the thing that locally describes the curvature of space-time. I'm now going to get a little bit more technical, but I think this is important to get some sense of. If you slice space-time into space plus time, with time going up and space running horizontally, this is curved space-time, not necessarily flat. Once you've done that slicing, this is like picking a reference frame in special relativity, inertial reference frame. You have to do the slicing first, and then the electromagnetic field tensor splits up under this slicing into an electric field and a magnetic field. And we can visualize these with field lines, such as these magnetic field lines around the Earth that are so familiar to us. Similarly, if you take the Riemann curvature tensor in relativity theory, and you slice space-time up in this way into space plus time, it decomposes into two, what we call in mathematical physics, two irreducible tensorial parts, two three-dimensional entities. The tidal field, EJK, that I've already talked about, which is sometimes called an electric part, that's a gravitational analog of an electric field, and a gravitational analog of a magnetic field, another symmetric trace-free tensor. These are what these are in terms of the reference frame associated with the space, this slicing. The EJK is this time, space part of the Riemann tensor. BJK is the dual of the Riemann tensor, is shown here with epsilon being the Levi-Civita tensor. But these details are not terribly important. The important thing is that EJK describes tidal accelerations in just the manner that I explained before. that is the tidal field. BJK describes differential frame dragging. So if I have a gyroscope at this point P, another gyroscope at that point Q, the gyroscope at P precesses relative to inertial frames at Q. So you have the gyroscope here, up here, its axis is precessing relative to inertial frames down here at Q by an amount in angular velocity of precession that is the product.
Okay, it seems we might having a technical difficulty. Just hold on for a second, please. Okay. Okay, we lost Kip as announced at the beginning, so let us just please wait for a second. In the meantime, let me announce that we are looking for law physics coordinators. So if you are interested, you can send an email of interest. Then just give me a second. I will call Kip.
Okay, as Alejandro said, announced it just recent. In the meantime, that we are contacted Kip again because he told us that he may have some issue with the internet, but this is normal in webinars. But in that sense, the announcement that Alejandro said that was we're looking to have new coordinators, as you might see, to organize the law physics could be it's very nice, but also it take time. So, and we know that there are many of you that are very enthusiastic, that are willing to also to lead the project and help us to keep going with this idea that is very nice to connect different people from part of the different part of the world, especially now in these times that we have the COVID pandemic around us. It's very important to keep going with this kind of project. So if you are enthusiast, you can write us. Our email is lawphysics@gmail.com. So you can write that, and we are gonna start to chat with you, to talk with you, to know if to evaluate a little bit about you, if you can help us or not. But in principle, there is the opportunity to also participate in this project that is very interesting and allow us to meet a lot of people. That is one of the nice things that we have done during all these 5 years of law physics. So, of course, everybody is welcome also to participate, but also the ones that are really interested also we can collaborate with us to coordinate the webinars. Okay, I guess maybe Alejandro soon enough is gonna contact us. So I don't know if the guys, meanwhile, we have to thank a lot of the people in YouTube for following this transmission. And of course, if you have any comments or question to the very interesting talk that Kip Thorne is giving, you can just to write it down in the okay. Kip Thorne is back.
Kip is back.
Okay.
No.
Cool, we're back. This is wonderful. Okay. Yes, Kip, we can, let me see. We can see you at least. We cannot hear you. Okay,
you cannot hear me?
Yeah,
Can you
now
hear
I can
me
hear
now?
you. Yes.
Okay, my apologies. Am I now connected back in?
Yes.
I'm going to.
You can share your
Okay.
screen again, please.
Okay, I'll share my screen again. Just a moment here. Okay. Can you see my screen now?
Yes.
Okay.
Yep. Now it's full screen again. Thank you.
Okay. 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 Can you hear me all right now?
Yes, we can.
Okay. So the problem is that too little of the space-time geometry is depicted in this way. So we devised this new way to describe, to visualize the Riemann curvature tensor. A piece of it is the tidal field. It's familiar that the moon raises tides on the Earth, and in terms of the tidal field, then, as I described before, the principal axes, the eigendirections of this tidal field are the directions of stretching and squeezing. And so it is useful to introduce the integral curves of the three eigenvector fields of the tidal field. And they describe then the directions along which there is stretching and squeezing. And for the moon and the Earth, the moon has then Tendex lines, which are these integral curves, Tendex lines that stick out of the moon, pass through the Earth, and they stretch the oceans along these red Tendex lines. And then there are blue squeezing Tendex lines that go around the moon, and they squeeze from the sides. And these are then the integral curves of the eigenvector fields of the Tendex, of the tidal field. Each Tendex line has an eigenvalue, ENN, that we call its tendicity, and that is the relative acceleration, the acceleration, difference of acceleration on the two sides of the Earth, divided by the height, the diameter of the Earth, is this tendicity. So this is just a new way, but a very useful way to think about tidal forces in terms of these Tendex lines and their tendicities. For a fast spinning black hole, the Tendex lines are rather interesting. There are squeezing Tendex lines that go out of the north pole of the black hole and around the black hole and back up into the south pole of the black hole. There are stretching Tendex lines that emerge from the black hole in the equatorial regions like this. And so there's a stretching along those Tendex lines, a squeezing along these blue Tendex lines. Then there are blue Tendex lines that spiral around, going up away from the black hole and similarly down from the black hole. So a very interesting pattern of this sort. And I like to use the word Tendex to describe a collection of Tendex lines with large tendicity. And so there's a Tendex that sticks out, a fan-shaped Tendex that sticks out of the equator of the black hole, and these poloidal Tendexes that go around the black hole like that. And those are the things that do very strong stretching and very strong squeezing. Now, similarly, we introduced the phrase vortex lines outside a black hole, as the vortex lines are the integral curves of eigenvectors of this frame drag field. But the simple way to describe this is if I place my wife above the black hole, we know that frame dragging causes a differential precession where a gyroscope at her feet will precess in this direction relative to a gyroscope at her head. That is this stronger precession here. Space is dragged into an angular velocity of whirling down here that's stronger than up at her head. So there's a differential precession that basically twists my wife, twists her feet around in this direction and relative to her head around that direction. So it's a twisting of space, basically. And this twisting is guided by these vortex lines. So you have a counterclockwise vortex of twisting space sticks out of the North Pole. A clockwise vortex sticks out of the South Pole. And this is the overall pattern of stretching and squeezing. And if you want to see this discussed in a textbook, well, of course, this is sufficiently new. The only textbook you'll find it in at the moment is the textbook that I recently wrote with Roger Blandford called Modern Classical Physics. So you have a counterclockwise vortex of twisting space sticks out of the North Pole. A clockwise vortex sticks out of the South Pole. Now let's look at a head-on collision between two black holes. And I'm going to just color code the north pole of this black hole where I'm afraid I have these reversed around. Let's have the clockwise vortex sticks out of the north pole here. The counterclockwise sticks out of the north pole there. And as they collide and merge, you wind up with a merged horizon that has 4 vortices sticking out of it. And these vortices robustly retain their individuality as the black hole then subsequently vibrates. So let's watch what happens. Here is the clockwise vortex, it's blue. The black horizon oscillates, it becomes counterclockwise, then clockwise, then counterclockwise. So the vortices sticking out of the black hole, they exchange vorticity as they fight with each other during this black hole merger. Blue oscillates between blue and red as these vortices fight with each other. When you look more closely, what you see happens is that there's a reconnection of vortex lines so that once the merger has occurred, at a moment when we see the color blue and red on the horizon, you have this clockwise vortex coming off the black hole, swinging around and attaching to the black hole on the back side. This counterclockwise vortex goes around, reattaches to the black hole on the back side. And as the black hole oscillates, when the horizon goes green in this visualization, these vortices pop off of the black hole. They embrace each other in numerical simulations. They create tori, and these tori travel outward away from the black hole, one after another as the oscillations gradually die out. It's rather remarkable that something called the Bianchi identities in general relativity, when you go to an inertial reference frame, a freely falling frame, say, a local inertial frame, they look just basically like Maxwell's equations. The time derivative of the tidal field is the curl of the frame drag field symmetrized, because these guys are both symmetric trace-free tensors. And similarly for the other Bianchi identities. So these look just like Maxwell's equations. So not surprisingly, as these vortices, these toroidal vortices of stretching of twisting space travel outward, you have a moving B field. They induce an E field, a tidal field of stretch and squeeze. And the Tendex lines of stretching reach around the torus like this. And the Tendex lines of squeezing reach around the torus's short direction. And these, in fact, are gravitational waves. They travel outward into space and ultimately reach the Earth, and it would be seen by LIGO. If you have an orbiting collision, a more astrophysically more realistic one, then these vortex lines get dragged around behind themselves and behind the black hole as the black hole spins. And once it's merged, they form spiral arms like this. And as these spiral arms travel outward, they have tendencies of stretching and squeezing space that are created through those analogs of Maxwell's equations. And you get gravitational waves then, intertwined vortices and tendencies of stretching and squeezing space and twisting space, traveling off into the universe. I'm going to just move on through this since I've lost some time. These are the actual patterns in the equatorial plane of the merged black hole, the actual patterns of the vortices and tendencies sticking out of the black hole. But you have then gravitational waves produced by vortices that are attached to the black hole. But you also have tendencies that are attached to the black hole, a squeezing tendex around this narrow neck when the two horizons have merged, stretching tendencies sticking off of the ends. And as this merged black hole tumbles, is because these two black holes were orbiting around each other, these tendencies stretch outward like that in spiral arms. And as they travel outward, they create vortices of twisting space entwined with themselves. And this gives you Tendex generated gravitational waves generated by tendencies that are attached to the black hole. So there are two types of gravitational waves in a black hole collision. Vortex generated waves generated by vortices of twisting space attached to the black hole, and tendencies of stretching and squeezing space generated by tendencies attached to the black hole. These are the vortex lines associated with the vortex generated waves. These are the Tendex lines associated with the Tendex generated waves late in the merger when the distortions of space-time are settling down into those of a curved black hole. And the patterns are almost identically the same. So there is a near duality between vortices and tendencies, between tidal forces and frame drag forces in black hole collisions, which is really quite a surprise and very interesting aspect of geometrodynamics. Of course, the key aspect of this is that LIGO and Virgo now are observing black hole mergers. Numerical relativity calculations are done to compute the gravitational waveforms for various spins of the black holes and relative sizes of the black holes. And then observers go in, they see gravitational waves, they match the observed waveforms with the theoretical waveforms. And having done that, they can go in and look at the numerical relativity simulation to see just what is the geometrodynamics that produced the observed waves. So far, LIGO and Virgo have seen 46 black hole collisions discovered by the LIGO-Virgo team. And there are an additional half dozen that have been discovered by other people looking at LIGO and Virgo data, which are now public. So you can go in and search in the data and find your own black hole collisions if you're clever enough at data analysis. And the waveforms that have been seen, I speculated in 1984 that they would be quite rich waveforms. In fact, they're far simpler than we ever expected. And the reason is that the disturbances in a black hole collision depart very quickly. So there's just not time for rich geometrodynamics to show up in the waveforms themselves. There, however, is hope that was coming to us from work by Juan Yang, Aaron Zimmerman, and Louis Slaner in 2015, that if you have a very fast spinning final black hole after a merger, the shape of the throat in an embedding diagram gets very long. And it is possible then for perturbations, for gravitational waves that are being generated to be trapped in this long throat, trapped long enough that you get nonlinear wave-wave coupling that will generate rich geometrodynamics in the gravitational waves themselves if they're trapped long enough in this throat before they escape to interact with themselves. And so we have a hope that in the future, such mergers might be seen and we might see the analog of two-dimensional turbulence, it turns out. This is a very interesting paper worth going and looking at. So in summary, I've talked about 4 arenas for geometrodynamics that I have picked out that show very interesting behaviors. Geometrodynamics that's chaotic near singularities. In imploding waves, you see in geometrodynamics the analogs of what you see in phase transitions, scaling, and critical behavior with critical exponents. Colliding black holes, where you see these dynamics of interacting vortices and tendencies. And gravitational wave observations, where we have, just from the fact that we have such good agreement between the observed waveforms and theoretical waveforms, we have evidence that what you see in the simulations really is happening. And all, however, I suspect we've barely scratched the surface in exploring geometrodynamics, and I see this as a very interesting area for future research. Thank you.
Perfect. Thank you very much, Kip, for this lovely talk. So let me go and start with a few questions. Let me start with I think one of our guests here, Isabel Cordero Carrion, has a question. Could you please turn off your camera and speak. Thank you. That's a start.
Yes. Thank you, everyone who organized the seminar and Kip for this wonderful talk. So I just have a maybe very naive question, but I wanted to take the opportunity. So in the evolution of the relativistic magnetohydrodynamic equations, you assume in the ideal case infinite conductivity. And now there are some simulations including this non-infinite conductivity, but a finite conductivity. As you mentioned that this space-time seems to behave somehow like the electric and magnetic field, do you have or do you know about the similar behavior of a metric of space-time when you include somehow this finite conductivity, so the similar to a non-ideal gas in the metric of space-time? Thank you very much.
So there are some significant differences between the gravitational and the magnetohydrodynamic behaviors. In the magnetohydrodynamics, you can get reconnection of field lines only because of finite conductivity. If it, in perfect MHD with infinite conductivity, field lines are frozen into the fluid and they don't reconnect. In general relativity, you get reconnection in vacuum without having to have any finite conductivity. And this does happen in the black hole collisions where originally the vortex lines that guide the twisting of space, they go out of the north and south poles of the black hole and off to infinity. But as the black holes get close to each other, they reconnect. And they wind up going out of one black hole and into the other black hole. And then when the black holes actually merge, they then are connecting two different spots on the single black hole. And so it's fundamentally different in that way. The analogy is surprisingly good. It's much better than I would have expected, but it's far from a perfect analogy.
Thank you very much.
Thank you, Isabel. Thank you, Kip. Okay, so let me continue with questions over YouTube. So the first one comes from Parth. Could the spikes in numerical simulations of chaotic singularity come from machine precision errors?
Come from what?
Machine precision errors?
No, because they're now understood analytically. And they arise from the fact that there's not an absolutely perfect decoupling between what's going on in two different observers who are moving toward the singularity along geodesics, initially parallel, but there's geodesic deviations that are being pried apart. But the decoupling is not perfect. And so these things arise, if my memory is right, I'm having to go back about 15 years. If my memory is right, they arise from a slightly imperfection in that decoupling.
Thank you.
But at least they are understood analytically.
Thank you. So there are two questions that are a little bit related. One is from Damascus Patalets and Samuel Bueno Soltau. And they want to ask about the state of art of our knowledge about what's happening into the black holes. Perhaps that person means inside the black holes. Is it still the same after LIGO and the Event Horizon Telescope observations?
So neither LIGO nor the Event Horizon Telescope can tell us about what happens inside the black hole. The interior is, in classical general relativity, the interior is truly decoupled from the exterior causally. And so the place where we learn about what goes on in the interior has to be through analysis of the Einstein equations. And there are changes in our understanding going to occur soon through numerical relativity. The numerical relativity community focused very hard on being able to simulate the generation of gravitational waves for LIGO and Virgo. But now that all of that is quite mature, a number of groups are turning to other kinds of problems. And a few people like Franz Pretorius have been focusing on other kinds of problems anyway. But there now more and more numerical relativity is spreading out into other kinds of problems. And it is Pretorius and others who are now exploring numerically what goes on inside of a black hole to test whether or not the things that have been deduced by analytical calculations, which are largely perturbation calculations, whether they really, whether we really do understand it properly. And so watch for those results. Hopefully within the next several years, we'll have a much better understanding of whether or not what I've told you is right.
Cool, thank you. Let me continue over YouTube. There is another question from Subayu Bakchi, and he says, or the person says, as mentioned, there are two types of gravitational waves, the vortex generated and the Tendex generated. Are these the two polarizations of gravitational waves? If not, how do we distinguish between them in observation?
So the two different types are not associated with polarizations. Both you have two polarizations for a gravitational wave. That is something quite separate from these two different ways of generating the waves. The two types of waves have different polarities, different behaviors under inversion, different parities. So it's analogous to what one sometimes says that you have a similar thing in electromagnetic waves, that the parities of waves that are generated by a magnetic field in the near zone. If you have a magnetic field in the near zone that oscillates, it generates electromagnetic waves that can have the opposite parity, what you get from an electric field that oscillates in the near zone. So you see it in the parity of the waves, as well as in what it is that's attached to the black holes that's generating the waves. The fact that they have opposite parity gives rise to something called superkicks. Once the black holes have merged and you have this near duality between the vortex generated waves and the Tendex generated waves, the waves two types of waves may superpose constructively in the direction, say, going down the south pole of the black hole, away from the black hole in the southern direction, and superpose constructively going up off the North Pole. And so because of constructive superposition in the one direction and destructive in the other, you wind up with a huge gravitational wave burst going out the North Pole and a very weak burst out the South Pole. So there's a huge momentum transfer in the northern direction, very weak momentum transfer in the south direction. And so the black hole is given a very large kick, a so-called super kick that was discovered, I think, originally by in numerical relativity simulations. I think it was by Manuela Campanelli's group at University of Texas in Brownsville. And these super kicks then are really a great astrophysical interest, but they are made possible by this opposite parity of the two types of gravitational waves, which means that they will superpose differently in the opposite directions.
Okay, thank you. And I think Mauro's Cambiaso's question is related. Hey all, thanks Kip for the great talk and organizers for the great work. Is there a chance for Tendex or vortex lines to pitch? If so, what will be the observable consequences of that? So I believe it might be related to the kick. Is it observable then?
So is it possible, again, is it possible for them to what?
To have the observable consequences, like if those kicks will be observed and what you were mentioning.
That's right. So the kicks are so strong that they can kick the remnant black hole out of the galaxy in which it lived. And so, the answer is yes, there are observable consequences. There is speculation that one such kick might have been seen. There is one of the black hole mergers that was recently announced by LIGO and Virgo. It may have been seen also by as a transient electromagnetic emission by sometimes my mind goes blank trying to remember names, but by the group at Caltech that looks at transient emissions, or a collaboration that is started at Caltech. By Sri Kulkarni. Anyway, so it's possible that there is one recent black hole merger that may have been seen electromagnetically, and that electromagnetic emission is speculated to have been created by the merged black hole moving out of a high density region through a super kick. And so I probably have this all garbled. I'm trying to remember details of something that I shamefully have not read the papers. I've just heard about it. So go in and look and see. You will find anyway some discussion of a possibility that a super kick has been seen. But, and you now have a bad example of somebody who is trying to talk about something that he hasn't read the papers, and so I've probably garbled it up. But it's a very interesting work, very recent work, yeah.
Okay, thank you. We still have lots of questions in the YouTube, so we will see how we do on time. But for the meantime, I think Joel has a question.
Thank you. Yes. Thank you very much for the talk. It was fantastic. So my question first goes in the direction of this Tendex. So this Tendex are what generates the jets coming out of the black hole. Would that be the reason for having the jets? Because you have the accretion and then you have the jets going in both directions, right? So this idea of having the spiral around suggested me of the jets. And if that was the case, then what would happen during the collision, right? Like you showed that these orientations would change. So what would we get? Something like a pulsar or something?
So the Tendexes do this stretching and squeezing. So the kinds of jets that they can produce are not the ones that are seen by radio astronomers sticking out of black holes, but rather these are seen in computer simulations where a star gets close to a black hole and is torn apart and stretched out, and a large fraction of the stellar matter is ejected into interstellar space. The remaining matter is sucked down and forms an accretion disk and then spirals into the black hole. We don't have yet visualizations of this happening, though we may get it someday from Event Horizon Telescope or at some successor. But you do see this in lots of simulations, and you go on the web and see simulations of where a star near a black hole is just stretched apart, torn apart, and then some of it is thrown out in a sort of a spiral arm, but ejected out, and the rest goes down into the black hole. The jets that are seen by radio astronomers are generated electromagnetically and not through gravitational forces. And so they're an MHD phenomenon along the lines of the first question that I was asked.
So in that case, those jets are just by angular momentum. They're just produced in that way.
Well, so those jets very likely are quite possibly energized by the spin energy of the black hole. The so-called Blandford-Znayak effect. Basically it is the frame drag field that then gives you differential precession. But it's a differential precession then that takes a magnetic line, not a gravitational magnetic line, but a real magnetic line, field line that, say, sticks into the black hole. And it basically sets that line into motion, a whirling motion as the black hole spins. And the differential precession then causes it's whirling around because it's tied to the spinning black hole, but farther away where space is not spinning, then it's being dragged around and it's generating an electric field as it's dragged relative to inertial frames far away. It's not being dragged relative to inertial frames near the black hole because of this differential precession that is near the black hole. It's just attached to the black hole, but farther away, it's being dragged around relative to inertial frames, and that generates an electric field. The electric field accelerates the jets. And so the mechanism is fundamentally due to an interaction between a Maxwellian magnetic field and the frame drag field that I've been talking about. So it is mixed between the two things. Once the jet gets going, it's purely electromagnetically, but the power generation is an interaction between the frame drag field that I was talking about and a real magnetic field.
Okay, great. Thank you very much.
Okay, and now Roberto is going to help me with some questions over YouTube.
Yes, first of all, Kip, I would like to thank for being here and all the nice talk, in fact. But yeah, we wanted, I mean, in principle, I had the same question than one of the people in the audience wrote in the chat, so we can take advantage and make it for you this question. That the question is from Maria Jose Guzman, and she is asking if could we expect evidence of physics beyond GR through the gravitational wave astronomy in the near future? What is your expectation about I mean, GR is super nice, but it would be better to have beyond GR effects.
I hope so. I don't think so, but I hope so. I'm always hoping for GR to break down, for standard physics to break down, because that brings us into a very exciting new era for research and for understanding the universe. But I'm not optimistic. When the LIGO Virgo team does data analysis, they very carefully compare with the predictions of GR and search for deviations from GR. And they're able now to do searches with rather high precision for some kinds of deviations from GR in their data analysis. And so, for example, when there's discoveries announced by the LIGO Virgo team, there's usually a paper that announces what's been seen and a companion paper that announces the new tests of general relativity that are done with this as part of this discovery. And so these things are going hand in hand. And so I hope that we do see the deviations from GR, but they've not been seen yet.
Cool, thank you. So Nico Yunes has...
Maybe it's worth just noting, in case people are not aware, that just about a week ago, the LIGO Virgo team released a new catalog of gravitational wave sources, the so-called O3A. It's from the third observing run, so O3, it's the first half of the third observing run catalog. And there is an associated paper on test of GR with the signals that have been seen in that catalog. And that catalog contains a number of gravitational wave observations of black hole mergers that had not been discussed in any detail previously. So it's a great richness of new information in that catalog, including tests of GR.
Thank you. So Nico Yunis has a question.
Hey, Kip. Thanks again for the great talk, for agreeing to do this. Yeah, so my question is perhaps a little bit beyond what you discussed just now. I'm just curious about what you think the biggest question that remains on the theoretical realm within gravitational physics is, and what you think the next big observational discovery that we just have not gotten yet will be.
I don't think I have any better wisdom about these things than you do, probably worse wisdom. Because you're younger, you have a more open mind and you keep track of what's going on much better than I do. In case you don't know, I'm spending most of my time these days trying to write poetry, so I'm not as in touch with what's going on in the world as you are. But I do still, as I have for a long time, think that the most exciting area that we're going to explore with gravitational waves is primordial gravitational waves, which will not likely to be seen by LIGO, but will be seen, I'm pretty sure, indirectly through polarization of the cosmic microwave background, and then later by a successor mission to LISA. I really look forward to seeing what information they bring about the earliest moments of the universe. On a shorter time scale, I do think it's very likely that the most exciting thing is going to be to see a signal of a type that was not predicted. And ultimately, in struggling with trying to understand that signal, recognizing there's something in the universe that we had not expected.
So. But do you mean like a system that we expected, but with properties that are strange, like, you know, a binary black hole that's maybe too massive, or like an eccentric signal, or do you just mean something completely unexpected that
something completely unexpected? Something completely unexpected. I have been struck by the extent to which, when new electromagnetic windows were opened onto the universe, completely unexpected things were seen. Of course, this was in an era when we knew much less about the universe than we do today, but the universe looked very quiescent, unchanging, except for an occasional supernova electromagnetically. And when radio astronomy came on the air, suddenly you saw colliding black holes that had been missed electromagnetically, not colliding galaxies, which had been missed electromagnetically. And you saw jets sticking out of galaxies, and a lot of violence that had never been seen before. And X-ray observations and gamma ray observations brought surprises. Gamma ray bursters, which were a complete surprise and a great mystery for several decades. And so I've continued to hope that there will be something like those that were basically totally unexpected. We haven't seen it yet, but it's still early days. It's observations have only been going on now for about 5 years, and with the detectors offline most of the time. So that's my hope.
Okay, thank you. And now my turn. So I always found like remarkable the interaction of analytical calculations, the computer simulations, and observations. Could you please talk about this synergy and how it has evolved over time? And in particular, I'm curious about how these simulations were perceived actually back in the day, because perhaps people didn't believe what computers were saying or what were they getting. Could you please tell us about a little bit of that, how that happened?
I think computer simulations first started to play a big role in astrophysics with simulations of supernovae. And that has been quite interesting, because you do the simulations, then you go to try to understand what's going on analytically. And Hans Bethe was superb at this. And you get some insights, and then the simulations are done further, and it turns out that in that case, you have competing effects with neutrino transport, for example, and the equation of state phenomena and shock waves, competing effects that are all of a magnitude that they're influencing what's going on. And it turns out it's been very hard to sort out what happens with the simulations or with combined simulations and analytical calculations. The area I'm most familiar with myself, of course, is this stuff with vortices and tendencies. And there it is rather clean. We knew about frame tracking. We had never thought about trying to visualize the Riemann tensor until we saw these vortices in our simulations. It was, and so once they were seen in the simulations, then you could go back and understand it analytically. And so the things I've described about vortices and tendencies, they are from going back and forth between the simulations and the observations, but it was totally triggered by simulations that opened up our eyes to new phenomena. This is precisely the same thing with the critical behavior in gravitational collapse. Critical behavior in implosion of waves that Matt Choptuik started. We had no idea there was this kind of critical behavior until Matt did his simulations. Once the simulations were done, people could go in analytically and start to understand them. And a rich interplay between the analytical calculations and the simulations. So in relativity, I think there's been a lot of that very productive see stuff first in the numerical relativity and then sort it out through combined simulations and analytical calculations. It's a little cleaner in relativity than it is in astrophysics. In astrophysics, you have so much more going on with shock waves and magnetohydrodynamics and imperfect magnetohydrodynamics. There's so much more going on that it's harder to make this interplay work as well as we do in numerical relativity.
Okay, thank you. And the last question, which is always for the early career scientists, and I'm going to combine those questions that we always get, is what would you like to have known before starting your academic life? Or what did you do at that early stage regarding research or like in academia that ended up being very beneficial for your academic career? So this is for the early career scientists.
I think I've learned a few lessons over my career that I think are valuable. One was that although we tend to focus very narrowly in our research in order to make really good progress, key ideas often come from connection to some other field. And so it's very important to spend some portion of your time, 10, 20% maybe, getting a broad understanding and maintaining a broad understanding of what's happening in adjacent areas. Jakub Borisovich Zeldovich is one of the really great astrophysicists of the 20th century. He would get up at 4 a.m. in the morning. He would spend the first 2 hours of his day reading the literature and thinking about stuff that was not in areas in which he worked. Now, this is a much larger fraction than I would ever advocate, but he would spend 2 hours just reading what was going on in other areas and thinking about it, and building up a great lore of stuff that would wind up, some of it being useful in his own research. Richard Feynman would do similar kinds of things, though it was, in his case, it was more typically hearing about something, going in, doing a calculation of his own in order to understand it. And he had built up this great storehouse of things he'd calculated but never published that it turned out to pay off in the end. And so I recount some stories about this in the preface to Feynman's little book on gravitation. So I think maintaining contact with other areas, adjacent areas to those that you're working in, and even farther flung areas, can have huge payoffs in the long run. So, I mean, in my own life, in my own life, an example is one of my students being in touch with what was going on in fluid mechanics and bringing in mathematical techniques from applied mathematics and fluid mechanics that were crucial for understanding radiation reaction.
Thank you very much. Thank you for this lovely webinar. There are still lots of questions that unfortunately we cannot ask. However, as you mentioned that you're writing poetry, so many people are writing us and emailing us, where can we read your poetry?
So I have a book of my poetry and Leah Halloran's paintings that will probably not come out until 2022. There is an excerpt in the October Scientific American, just a short excerpt of one of her paintings and a small portion of my attempts at poetry. But I'm just having fun. But there are a number of missing paintings, and it's going to take until next summer to get the paintings all under control. And then it'll take the remaining 9 months probably until the book is out. So just be patient.
We'll do. Thank you very much. And we also thank all our viewers and the people. Don't forget to subscribe to our YouTube channel and stay tuned for the following Law Physics webinars. Thank you very much.
Thank you. My pleasure.
Thank you.